One last thing I wanted to talk about before we leave this modern unit, something I don't know a better way to call it, so I'm going to call it observing a quantum system, like what happens when you look at a quantum system, and then a little bit about Heisenberg's uncertainty principle. An artifact of this wave-particle duality, an artifact of the wave part is quantum systems are allowed to be in superposition. Uh, um, and then an artifact of that is the superposition falls apart if we observe the state of the system, which is kind of weird. Um, the best way to think about it, or I think the best way to think about it, is to go back to the double slit experiment, especially if we did the double slit experiment with electrons or other things that we tend to think of as particles. In the double slit experiment, the particles are in a superposition of going through the left slit and the right slit at the same time. That's a way to explain why they know there's two slits. That's a way to explain why we get an interference pattern. This wave-particle duality, as a wave, they travel through both slits, but then as a particle, they locally show up at the detector. So a way to explain the double slit is to use the idea of superposition. The particles are in a superposition of going through both slits at the same time. If we were to get fancy and try and take a closer look at the double slit experiment and put detectors by the double slit to see what's actually happening, so to make an observation about what the particles are doing, as soon as we add detectors, then this superposition thing falls apart and we don't get an interference pattern anymore. If we were shooting electrons through a double slit and we weren't peeking at the electrons, just shot them through, we would get an interference pattern because of superposition. But if we cheated and put a detector by one of the slits to see which slit the wave is going through, this wave-particle duality, this quantum particle is going through, when we put a detector in it, we force the system back into particle mode by trying to find out where that localized particle went. So kind of weird, but when you observe a quantum system, it loses its superposition thing and kind of collapses into one form or another. Schrodinger came up with this thing they called the wave function, and what quantum people say is when you observe a system, the wave function collapses. Basically, it loses its wave-like thing and just goes back to being particles. So if you were to observe a double slit experiment with detectors at each slit, you wouldn't see the wave nature, you'd see the particle nature. The wave nature would have collapsed. When Schrodinger came up with this weird argument, well, not weird, when Schrodinger came up with this argument, to try and explain it, he came up with this weird thought experiment. Didn't actually do it, no cats were injured, but he had people imagine a box. He had more detail. He talked about a box with a quantum thing inside, and the quantum thing could either decay or not decay, and if the quantum particle, if the quantum system went one way, poison would be released, and if it went the other way, the poison wouldn't be released. So since it was based on something quantum, and quantum particles are allowed to be, quantum systems are allowed to be in a superposition, then this box with the poison in it was in a superposition of both aspects. Maybe it happened one way and the poison was released, or maybe it happened the other way and the poison wasn't released. Because it's quantum based, we could say that it's in a superposition of both. That means the poison was released and not released, which means the cat is both dead and alive. It was just a thought experiment he came up with to get people talking. It's one we still refer to today, and that's basically the outcome. The cat is allowed to be dead and alive at the same time. If we open the box and observe it, then that duality, that superposition part, the superposition part disappears, and obviously the cat would be one way or the other. And an argument or some reasoning behind observation affecting quantum systems. It just is an aspect of quantum. One argument or one way to rationalize it is whenever we observe something, to observe it, we use light, whether it's visible light or ultraviolet light or infrared light. But basically, to see something, we bounce light off of it and then collect that light in a detector or our eyeball if we're talking about us. Sorry. If we're looking at quantum things, though, quantum things are very small. So normally, bouncing light off something doesn't change the thing we're bouncing light off of. Like if I wanted to observe a car driving down the road, I just bounce light off the car, find the front of the car, locate the back of the car using the light, and I can see the car and that has absolutely no impact on the car. But if we're looking at something tiny like a quantum thing, then the act of bouncing light off of it, from what we learned earlier in the unit, light, even though we tended to think of it as a wave, the Broglie wavelengths, the momentum idea, light carries momentum even though it's massless. So if we observe small things, the momentum of that light has the ability to change the thing that we're observing. So as well as like a wave function collapse that Schrodinger kind of talked about, observing a quantum system changes the quantum system, which is kind of a cool big thing. When I typed this a while ago, I was thinking about this trip to Amsterdam. My younger brother, right after university, or kind of in the middle of university actually, took a year off and went to Amsterdam. He just wanted to get out, and he actually had a contact and got a job. But it made me think, like some people say, oh, I'm going to go to Europe and find myself. Well, hopefully going to Europe changes yourself. That's a pretty life-altering experience. So kind of like using light to observe a quantum system will change the quantum system. In my mind, if you make a big statement like, oh, I'm going to go to Europe to find myself, going to Europe's a big thing. The act of doing that's going to change what you're trying to find. So I don't know if that helps make sense of the idea of observing changing as it changes what you're observing, but that kind of popped into my head when I was typing this note. What's neat about this idea that observation affects a quantum system is practically they use it in quantum cryptography. Cryptography is just basically a fancy word for encoding information. For example, in a non-quantum system, so maybe I'm on the internet and I'm making a purchase over some online vendor and I send my credit card information. Maybe it's through fiber optics, maybe it's over like coax wires, like metal wires. It could be a digital signal, whatever, like, but if I'm not using a quantum system, basically it's a complicated Morse code of zeros and ones. If somebody was clever, they could intercept that message, get my credit card information, and then as long as they could crack the code, they would have that information and they could take advantage of it. A quantum system is different. If we encode information using quantum technology, if someone were to intercept a message, so let's say I have a quantum encryption system and I put my credit card number in and I send it to a vendor over a quantum system, if someone intercepts that message hoping to read it and to get my credit card information, they can possibly intercept it. They could maybe crack the code, but as soon as they observe it, that will have changed the original message that I sent. So the people receiving it people receiving it would be able to tell that the data has been compromised. Then they could let me know so I could change my credit card, change my password, shut it down or something. But a big deal in quantum cryptography, it's not that you can't decode it, but the people that are sending the information would know that it's been compromised, which doesn't happen with the regular non-quantum information. If somebody hacks into my email, they don't change my system necessarily, so they could be in my email looking at things and I would have no idea. In a quantum system, if someone were to hack in and observe it, the act of observing changes the system, and therefore, as long as you're clever with how you encode the information, your receiver of the information would know that the system's been observed, would know that an interloper or a hacker's tried to take a look at it. Okay, completely different, but also kind of along the same lines is something that you may have heard called the Heisenberg uncertainty principle. I'm not going to be able to explain it very well. I'm going to do a little talking, then I'm going to refer you to some videos. The links to the videos won't work on the YouTube that you're watching, so make sure you open up the original Google slide deck and use the links there to watch the video. Basically, Heisenberg certain he did math to go with it, but the logic is, according to wave-particle duality, waves are a non-localized thing, so it's difficult to say where exactly a wave is. You can't really locate a wave because a wave is allowed to be non-localized, is allowed to be sort of spread out across a region. And then kind of tied into the particle part, to measure the speed of something, you have to observe it. So you have to get a measure of displacements over times. There's typically, when you're doing, like if we think of doing lab work, there would be uncertainties in knowing exactly how fast something's going. So it's a consequence of wave-particle duality, but because waves are non-localized, particles are localized, but there's some interpretation and some uncertainty in observing them. Because of that, there's literally a built-in limit in the universe to how closely you can know position and speed. You can't absolutely, with zero uncertainty, know position and speed. If we narrow it down and do let's say a lab or a calculation so you can figure out position very, 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 very closely, like with a very small uncertainty, the better you know the position information, the worse you're going to know the speed information. And the vice versa. If you do a lab to figure out exactly how fast something's going, as you narrow in and get more and more accurate with your speed, you're going to be less and less accurate with your position. It has to do with the local and non-local nature of waves versus particles. So I guess non-local nature of waves and the local nature of particles. I recognize that that's maybe not the best explanation. Heisenberg did a bunch of crazy math to go with it that I'm not going to try and duplicate, but basically there's a limit. We can't know both with a high degree of certainty. What I would like you to do is pause this, stop this YouTube video, and then open up the original Google slide deck, watch this Veritasium video. He does a neat job explaining it because he ties it back to the single slit, the experiment that we did in our wave optics lab. And then this TED Talk, this is another good one to listen to as well. That's the last little bit I wanted to make sure that we covered in this modern physics unit. So make sure you're on top of everything. And as always, email me if you have any questions.